Good afternoon. Today we will start a completely new chapter, and it will be the most important chapter in our course, and we will be talking about induction motors. We will have 4 lectures related to induction motors, since this is the most common machine today, and we will discuss its properties and control and many details. As you can see, we're trying to tape the lecture today, so if it will succeed, we will be posting the videos on the internet. Induction motors are the most common type of motors that you can find today. Induction motors were invented about 130 years ago by Nikola Tesla, 1888. And the reason why they are used is that they are very simple. The construction is very simple. When we have seen, for last 2 lectures, we have discussed DC motors. DC motors have commutator. They need mechanical contact between the rotor and stator. But induction motors, they have a very simple construction. Which means that they can be manufactured very easily. They are less prone to mechanical damage, mechanical wear, and they also have typically higher efficiencies. So induction motor is the most common motor today, although it is not the most efficient motor. We will see at the end of the class that there is something more efficient. It will be synchronous motors with permanent magnets, but then it's more costly because you need permanent magnets. So induction motor has a simple construction. It can be very efficient, but it's definitely less efficient than permanent magnet motors. Induction motors that we will discuss will be 3-phase and single-phase motors. We will first start with a 3-phase motor because it's easier to understand how this motor works. And I believe next week we will cover single-phase motors, which are a little bit more difficult to understand, but they work in principle in the same way. Today we will discuss the construction of a 3-phase induction motor, and I have also prepared a short video how those induction motors are manufactured. On this picture you can see the basic components of an induction motor. So from the outside it will have a shaft. That's where you connect the load. It will have a terminal box where you connect the terminal wires. It should have a nameplate, and we will discuss the nameplate values in detail as well. And here you see the end bells. Those are the places where you will find the bearings. The induction motor from the outside looks the same if it's a 3-phase or if it's a single-phase motor. The reason why an induction motor is so common is that we can very easily control the speed with today's electronics. It doesn't require any maintenance, so virtually all electric appliances that you can find will use an induction motor, with the exception of handheld tools, because handheld tools require low weight, and we will need a different kind of motor for that. So induction motors are used for stationary machines that don't care too much about weight, but they care about reliability and about low cost and low maintenance. If you have, for example, handheld tools like a drill, you need that it's light, and an induction motor of this kind would be very heavy. Although it would be quite good in terms of maintenance, but if you would have a drill that weighs 10 kilograms, then it would not be a good drill. So standard induction motors are used everywhere where we don't care that much about the weight. Here you have an example of a large induction motor. So induction motors, they come in various sizes. They can be produced for powers of 100 watts, but they can be also 400 kilowatts or 1 megawatt. So here you see an example of a three-phase induction motor. We will discuss the properties later. So here you see that's the motor itself, and that's the large version. Induction motors can also be used as a generator. So we can use induction machines also to produce electric power. It's typical to have such generators in small power plants. Large power plants will use permanent magnet or other kinds of synchronous motors. What are the components of an induction motor? So, rotor and stator. That's the same like a DC motor. But the construction itself is quite different from a DC motor. Here, the rotor, it doesn't have any winding. So the current that, or any commutator, the current that is created in the rotor is created by induction. We'll discuss that later. So there is no direct mechanical contact between some winding at the stator and some winding in the rotor. Everything is happening with induction. By the way, induction motors are also called asynchronous motors in some languages. So this is the rotor. As we will see in a few minutes, it is steel that is laminated. And the stator is equipped with windings, and it is also created by lamination. So the steel sheets are laminated, and in the case of a three-phase motor, it will have a three-phase winding. So the construction is completely different from the DC motor. So what are the basic parts of an induction motor? The rotor has basically the magnetic circuit, which are the steel sheets, and then it has a rotor winding, which is either really a winding from copper wire, or it is created from aluminum bars. Let's start with the rotor sheets. Here I have some examples of sheets for this kind of motor that you will have the chance to see. So those sheets are sheets from an induction motor. So we see it's steel. It's electrical steel, so high content of silicon. We want to reduce what? Why is it laminated? Friction? No. Yes, losses. What kind of losses? Yes, eddy current losses will be removed by, well, limited by laminations. So it's not solid steel, although it would work in principle also from solid steel, but it would have high losses and therefore low efficiency. So this is the rotor, and then the rotor that is completed looks like this. So this thing in the middle, that's the iron sheets, and this is aluminum in this case. And the aluminum goes in those slots, and it creates bars which act like a winding. I have here some examples, so let's take a look on this. By the way, this part acts like a fan. So when this turns, we will have airflow that will cool the machine down. So let's take a look on that. And I have also two complete rotors of an induction motor. So this is a small one. You see again the sheets are laminated, and this is where you would put the bearings. That's a small one, and here that's the larger one. Again, laminated rotor and aluminum bars acting like wires. So this is a little bit larger induction motor. Yes, it's quite heavy because iron is heavy, unfortunately. Okay, that's the rotor. The stator needs winding, and in the case of a three-phase rotor, a three-phase induction motor, it will be a three-phase winding. Here you see an example of a really large induction motor. We'll discuss that on the next slide, what is inside. But basically, we again need a magnetic circuit, and then we need windings. So the stator of an induction motor is again laminated. The sheets, they look like this. And the lamination here serves again to reduce eddy current losses. If you make it a solid iron, you will have high losses and low efficiency. You could have done the stator from solid iron in DC motors, because in DC motors we had DC magnetic flux, but here we will have AC magnetic flux. So in this case, both the rotor and stator are created from the same material, electrical steel. So this is what you see here. That's called a stack of the stator. So this is the sheet that it has been assembled together into a packet. And here in those slots is where you will fit the windings, as we will see in a few minutes on the video. So the copper wire will go in a specified pattern into those slots. And this white stuff, that's insulation, that serves to protect the copper wires from being damaged by the iron here, to prevent short circuit between the copper wire and this stator packet. So here you have examples of stator sheets, and then the completed stator is available here. So here this is iron, and here in the slots in the insulation layer we have windings, and since this is a three-phase motor connected in a star connection, we have three output phases that would go to the power network. So this is the stator that fits to the smaller rotor that you have somewhere around here. So I'll let you see those pieces. Where's the, yeah, it's this. No, you can keep it, but this fits inside of this motor like this. Okay, so the insulation layer that you see here, this white stuff, is either made from paper or it is made from plastics. That depends on the temperature where this motor should work. And the copper wires that will fit inside these slots are typically insulated by a thin layer of enamel, which is like a lacquer, that you apply on top of the copper wire, and this provides you the insulation. Here you can see an example of this machine, including the winding. So here, that's the iron sheets. This is the copper wire, and you see here this white stuff is the insulation. So this is an example of a single phase motor that has two windings basically, but a three-phase motor will need three-phase windings. The number of slots here that you have is given by the construction, by requirements for speed. So this specifies you what speed should the motor have, and as we will see, I think next week, the speed of the induction motor is a function of frequency. That's the main parameter. So when we want to control the speed of the motor, we will have a stepwise control if we change frequency or if we change construction. If we will be able to use electronic circuits to create some variable frequency, we will be able to have a variable speed drive. So now let's take a look in more detail on the construction of the motor. So here you see an example of the stator sheet. So this is the sheet of electrical steel. This is where we would place the winding. And those holes here, they serve to facilitate the assembly of the machine. So typically this is assembled in a stack, and this is where you put some kind of screws that will hold everything together, and then it's either mechanically assembled or today the sheets are welded together on the edge somewhere around here to hold it tight. So this is one part of the magnetic circuit, and we need a complete magnetic circuit into the motor to provide maximal torque. So here you see the assembled stator and rotor together. Here we have the stator, and here we have the rotor. So in the stator we have copper windings, and in the rotor we can have copper winding as well, or we can have aluminum bars that will be in those slots. The magnetic circuit is going through the iron, so the magnetic flux is created in the winding, so let's say somewhere around here, and it goes through the air gap, which is here, to the rotor, and then back to the field winding on the stator. The air gap here is the limiting factor. If you want to make a high torque machine, you need to make the air gap as small as possible. But on the other hand, if you make it too small, it may be very difficult to produce mechanically. You probably can make the air gap like 10 micrometers, but then you would have problems with how to manufacture that, or even with temperature expansion. If the motor gets hot, it may expand, and then you may it may fail. The rotor winding, I already told this, can be of two types: either really a copper winding or aluminum bars. When you have aluminum bars in this slots, it's very easy to produce We will see that in a few minutes on a video, that it's one operation. You melt aluminum, you pour that into those slots and you have a rotor. This version of the induction motor is called a squirrel cage. And it typically looks something like this. So this is an example of a squirrel cage rotor. And this picture is showing only the aluminum bars on the rotor. So there is not, the magnetic circuit is not shown, but you need to have it there because it will, if you would do it like this, you would have a very, very small torque. So here we see that we have a ring on both ends and that the rotor bars are connecting those rings. So this acts as a winding that is in the rotor, and those bars are placed in those slots. And we can also see that there is a slight skew of the rotor bars. And the reason why we have this skew is that this arrangement will provide you a more uniform torque around the revolution. So you have smaller torque ripple in the motor that is like this. In principle, you could of course make it straight, but then the torque ripple would be higher. This type of induction motor is the most common one. The squirrel cage motor is almost everywhere. It has a very simple construction, so it's very easy to produce. It will have quite good properties in terms of the torque speed characteristic. But once you made it, you cannot change the properties of the motor. So if you make a squirrel cage rotor like this, it will define you the parameters of the motor. If for some reason you need to change the properties of the motor during operation, then this is not a good type of motor. And in this case, you can use a motor with rotor winding. So those bars are replaced with winding, and by connecting additional resistors through rings, you can change, for example, the torque speed characteristic of this kind of motor. We will see that in action in some file. Here is an example of a squirrel cage rotor. So this is the shaft. All this rotor will go into the stator winding. Here you see this is the aluminum end ring on one side, aluminum end ring on the other side. This is the magnetic circuit, so this black part is the iron. And here in those lines are the slots where we have the winding, where we have this part, those rotor bars. Now we will take a look on the video where we will see how this is produced. The video is unfortunately in Czech, so I'll stop it from time to time and explain what they are doing. But we will see the manufacturing first of the rotor and then of the stator sheets. So let me find it. Okay, so that's like an old video from a factory here in Czech Republic. And we will see the production of motors for middle powers. So let's say somewhere between 2 and maybe 50 kilowatts. So, so this is the shaft. So the shaft, they produce it by turning. It's not so interesting, but in a few moments we will see the rotor and stator. But it has to start with the shaft, because then the rotor that you see here is pushed on the shaft. So this is the assembly of the rotor, but now we will see how the rotor is made, this part. So this is the iron sheet from electrical steel, and they will push it through a press, and they will produce the sheets of the material like you have somewhere here. So this is the packet of the rotor, and this is the stator. So it's one operation at a time. They press it at the same time, and they stack it into the correct height that is required. So this is rotor, and the previous was stator. So now you see he has inserted this packet into a machine where he will pour molten aluminium inside the slots of the rotor and press it inside. So it's in one operation. He has poured the bars inside those rings, and then here you see the blades of the fan that will provide cooling for the induction motor. So it's very easy to produce compared to DC motors. So now they are preparing the surfaces for the bearings and balancing the rotor, of course. So now this is balancing. So they started, the point should be in the middle when it's balanced, and if it's not, they will be adding or removing weight from correct positions. So now small weight has been added to the rotor, and it is balanced how it should be. So you see the rotor is so this will be stator, so that's the cover, and they will take the magnetic circuit, insert the coils inside, including insulation. Now this will be drilling of holes, tapping, and so on. Okay, so this is the assembled packet for the stator, and now we'll see how this is made. We'll first press it inside the casing.
Nalizováním se v podstatě uzavírá statorová linka. Ale dříve, než budeme sledovat zkompletování celého motoru, věnujme naši pozornost výrobě právě narizovávaného paketu statoru. Ta začíná přesně tam, kde výroba paketu rotoru.
So it all starts again from the metal sheets.
Vyrážejí se z něj plechy pro rotor i stator.
That's the assembled sheets.
Plechy jsou přesně srovnány, rysovány a mechanicky zajištěny.
So this is the assembled packet. Here you see the slots where the winding will go. This is, it holds together by those parts here, this part and this part. It's like a metal sheet that holds that together. Or you can have screws that go through some hole. Or today you can even weld it here with some laser to fix that in the correct position. Now they will insert insulation into the slots to prevent short circuit between the windings and the iron. So that's the winding. And either it's done automatically or, as we will see later, by hand for some kind of motors. It's a multi-layer winding. So here you see one layer, second layer, and so on. And let me go back. So this is a fixture where those are the coils that has been wound, and the motor, the stator, is here, and this machine will pull the winding inside of the slots. So now it's the stator, and now in the fixture this will move forward and will pull the coils inside. So now this is a holder that holds the winding in place. So when you pull the winding inside, there needs to be some free space so that you can pull it down, but this fixes the winding in the position. So it's like a wedge that you put inside of the winding. Now they will mechanically fix the windings here, the end parts, together so that they are not freely moving. And now they will put the rotor and stator together by pressing it, including the bearings. So that's the rotor. That's the bearing assembly. Now we will see that there is a fan at the end of the shaft to provide cooling, of course including some cover. So that's the fan.
Každý motor má proto svou vlastní účinnou ventilaci. Ochranný kryt nesmí samozřejmě chybět. Tím je celý motor funkčně hotov a pracovník výstupní
So that's testing, just to see if that works. Start test only, and only some selected motors are measured in a more detail. So all this was the Squirrel Cage rotor. And now we'll see how the wound rotor is made. So if you need to change the properties of the motor in runtime, you can replace the aluminum bars with copper windings and connect them to an external circuit. And now what you will see is the assembly of the rotor when it has coils inside.
Pro některé účely mají vhodnější vlastnosti asynchronní motory s vynutým rotorem.
So it's exactly the same principle. Here we see the magnetic circuit, but here in the slots we have windings that will be connected to rings so we can change it from the outside.
Bývají vyráběny v menších sériích, proto se vynutí zakládá obvykle ručně. Princip je obdobný, jak jsme už viděli u Statoru.
Okay, so this is the rotor, the winding, and it's a three-phase winding that is connected to those rings. And those rings are connected then through brushes to a terminal box that is outside. So compared to a DC motor, this is only a ring. It's not a commutator, so it doesn't have individual sections. It's easier to produce. You just have 3 rings and 3 brushes, and that's it.
Bývá vynutí takového rotoru končí na sběracích proužcích. Elektrický kontakt potom zajišťují.
So this is the assembly in the terminal box. So those are the 3 brushes that connect the rotor to a terminal box. And as we will see a little bit later, this allows us to change, this, for example, the torque speed characteristic of the motor to achieve a different startup torque than we would be able to do that with a Squirrel Cage motor.
Gardáče v restatorové části motoru. K výrobě patří také velká zkušebna, která umožňuje
Okay, that's just the testing. You will do a similar testing in the labs. And think we can go back to the construction. So this is the second type of an induction motor that is called a wound motor or wound rotor. Most of the motors have squirrel cages, so they are very easy, but they do not allow us to change the characteristics. One reason why we want to change the characteristic is, for example, we want to change the speed of the motor in a very small region, or we want to change the startup torque, and we want to limit the startup current. Today we can do that quite easily with a frequency inverter, but before frequency inverters were invented, this is how it was done, and it's still possible to use it to change the characteristics of the motor. Here we have an example of a rotor for a large induction motor. As you see here, we have the winding in those slots. So that's the winding, and it's inside of the motor. Before we go to the operating principle, I think now it's a good time to start with the bonus quiz, or with the lecture test, which will be related again to the last lecture. So I'm starting the Moodle test for DC motors, and you should be able to log in. So let me know when you're ready. It contains questions related to DC motors that we have discussed last week. There are 4 of them again, and then we'll go back to the operating principle of an induction motor. So, ready? Okay, so let me start the quiz. You should see the first question soon. So this is about the torque speed characteristic. Okay, so the torque speed characteristic of a separately excited DC motor is linear, and the higher the torque, the lower the RPM. Because if you load something, then the speed will decrease. It would be hyperbolic for a series motor. Question number 2. Okay, so a DC motor can be controlled by adding a resistor or by pulse width modulation, but pulse width modulation has highest efficiency. Resistor has losses, so the efficiency will be lower if you use resistors. Question 3 will come soon. So now this has multiple answers. Okay, so the speed of a DC motor depends on armature voltage, armature current, and armature resistance. So those three answers are correct. It can't depend on the rotor voltage or armature voltage frequency. We have a DC circuit, so frequency is 0. And why should it depend on the moment of inertia? The acceleration would depend on the moment of inertia, but not the final speed, since in steady state, the moment of inertia times change of speed versus time is 0. Okay, and question 4. I hope you will all have this correct. Yeah. Plus, I have said it like 3 minutes ago, so maybe I hope you will remember that. That's the last question. Okay, so a serial DC motor, hyperbolic torque speed characteristic.
So what is the answer?
Hyperbolic. Hyperbolic is the correct answer for serial motor. Serial motor has hyperbolic. So who was it that answered linear? Yeah. So separately excited. Linear, serial, hyperbolic. Yeah.
I just saw half the question and I thought it's the same as the first one.
No, it's not the same. Like why should it be the same like for the first one? No. From the whole Moodle test? I did. Well, try to refresh the page. I did not close the session. Yeah, because until I close the session, it shows you 0. Okay, so let's go back to induction motors. And we shall discuss the principle of induction motor. So, let's imagine we have a 3-phase stator winding. So here in this picture you see the winding in the stator slots, and we see that it's a 3-phase winding. Here we see we have a coil called A here and A here. So stator winding phase 1, phase A is over here. Then we have phase B here and here, and we have phase C here and here. So we have a 3-phase winding. The winding is powered with AC voltage. So here at the stator winding, we will see 3 sinusoidal voltages, 3 sinusoidals. So this is voltage, let's say in phase 1, VA. So this is voltage here. And in a 3-phase network that we are using to power this, the phase voltage in the other phase lines will be shifted by how many degrees? No, not 90. How much is 360 divided by 3? 120. So the voltage will be shifted by 120 degrees. So here we have 90, here we have 180, so 120 is somewhere around here. So this will be the second voltage. Let's call that VB. And the other voltage, the third, will be shifted also by 120 degrees. So let's mark it like here. So I will make only sections, but I think you can imagine 3 sinusoidal voltages. A sinusoidal voltage will create a sinusoidal magnetic flux. So if I would have only a magnetic flux or only a voltage in, let's say, winding A over here and over here, I would create a magnetic flux that is following the sinusoidal with the same frequency, but it will be only moving up and down. So it will only change the direction. If I add those 3 magnetic fluxes together, we will create a rotating magnetic field. So if you would add this together, you will see that the rotor, the stator magnetic field appears to be rotating. And it will have the same effect as if you would have a permanent magnet on the stator and you would move it. So now we have a rotating magnetic field with some frequency around the stator. And the rotor winding is standing still. We start the motor, we power the stator winding, the rotor is standing still. We have the magnetic rotating field, but the rotor winding stands still. And now we have a wire, and around the wire we have a rotating magnetic field. So what will happen in the rotor? But why will it spin? It will spin, but why? You have a fixed wire that's standing still, and you have a rotating magnetic field. So because of the change of magnetic flux, we will induce voltage in the rotor winding. So there will be an induced voltage that is being created in those slots in this winding. So let's see this thing, this image. So this is the rotor, those are the bars, and here we will have induced voltage in those bars. You see that the bars are connected by the end ring here, or it's a winding. So we have voltage on the bars, and since this is connected all together, we will have current. So there will be current that starts to flow in the rotor winding or in the rotor bars. And now I have a rotating magnetic field, and I have wires with current. And there will be a force that will try to synchronize this movement. So the rotor winding will try to follow the speed of the magnetic field that it created. But there's one problem. What would happen if the rotor will spin with the same speed like the magnetic field? Let me specify that. What would be the current in the rotor winding or in the bars? What? No, it will not be very big. Imagine, I have a rotating magnetic field on the stator, and now I'm moving the rotor with the same speed, like this. And we have said that the rotor current here is caused by induction, because the magnetic field is changing. And if the rotor is moving in the same speed, there is no change in the magnetic flux in the rotor, so induced voltage is zero and current is zero. So an induction motor will always have a lower speed of the rotor, because if it would have the same speed, there would be no torque and no current in the rotor. So for this reason, induction motors are also called asynchronous motors, because the rotor is always moving at a smaller speed than the magnetic field in the stator. Yes? Yes, it does have something to do with the stator windings. We'll see that later. It will influence the nominal speed of the motor. Okay, so here we see that the torque of the induction motor will depend on the difference between the speed of the rotor and of the stator magnetic fields. So the torque speed characteristic of an induction motor will have a specific shape, and the torque will be a function of speed. The three-phase winding that you can see over here can be connected either in a delta or in a star connection. Typically here you have the phases A, B and C, and in this case you see I'm going from phase A, and phase A now starts here, phase B starts here, and phase C starts here, and the common ends of phase B, A and C are connected at one point. So this is a star connection, but we could connect that also in a delta connection. As we will see, this will help us to limit the startup current, because we will see that an induction motor has a quite high inrush current. You turn it on and the current during startup can be very high. The reason why it can be very high is because when you start the motor, you have a very high difference between the speed of the magnetic field on stator and the rotor is standing still. So we have a high inrush current, and we will also discuss ways how this can be limited. So now I think I have discussed this. Okay, so here you see an image that will show us how the magnetic flux is being created. So here we see the magnetic flux that is created from the stator, and the rotor creates also its own magnetic flux, and it interacts together, and it will create the torque that the machine has. I think detailed explanation, including equations, that will help us to understand later the torque speed diagram and equivalent circuit diagram. But basically here you see the voltage on the motor will depend on the strength of the magnetic field times length of the rotor times the speed difference between the speed of the magnetic field on stator and between the speed of the rotor. So again, if the rotor speed would be the same like stator speed, then it would be zero torque, and we'll see that also on the torque speed characteristic. Let me show this. There is one very important property of an induction motor that is called slip. And slip is the difference between the speed of the rotor and between the speed of the magnetic field on the stator. So slip is defined by this equation. This is the synchronous speed, and this is the actual motor speed. And if slip is 0, it means this synchronous speed is the same like the motor speed, so it means the rotor is turning with the same speed like the magnetic field on the stator. No, the synchronous speed depends only on the frequency of the voltage, not on the amplitude. So here, the synchronous speed is given by the frequency, that's here, and by the construction of the motor, where here P is the number of pole pairs in the motor. So if I have a machine like this, so I have winding, one here, so A, B, and C. I have one pole pair, and if I power this with a frequency of 50 Hertz, then the synchronous speed will be 3000. So the speed of the induction motor depends on the construction and on frequency. So since the lowest number of pole pairs is 1, then the highest speed that you can achieve with an induction motor without any electronics for a 50 Hertz frequency is 3000. So this will be one way how we could change the speed of an induction motor. We could have more windings and we could switch them in operation, but stepwise. We can switch between one pole pair, two pole pairs, then probably 3, but it will be a very complicated construction. But the easiest way to control the speed of an induction motor will be to change the frequency of the power supply voltage. And this will require a frequency inverter, which we will cover in about 2 weeks. Back to the slip here. The slip is the difference between synchronous speed, which now we know it's a constant number, and between the motor speed. And we will see that the torque that the motor creates is a function of slip. So the higher the speed difference, basically the higher the slip will be, and the torque will be also higher, at least to some maximal torque, at least to some point. So now let's discuss in more detail how the torque is being created in the induction motor. So now we know that we have one magnetic field on the stator and another magnetic field created by the induced voltages in the rotor bars. So here, this magnetic field is coming from the stator, and it's frozen in one instant. So in one moment, I have direction of the magnetic field in the vertical direction. This is the rotor bar where we have the current flowing in, and the force that is being created between the wire and between the magnetic field is given by this equation. So the force that I create will depend on the current, will depend on the length, and will depend on the strength of the magnetic field. How can I influence all three of them? Well, current here can be influenced by changing the resistance of the rotor bars. So by using a different material, for example, or different cross-section, I can change the resistance in the rotor, and this will change me the force and hence the torque that I will create. Length, that's clear. If I make the rotor longer, it will have a higher torque because I will act on a higher distance. But obviously, if I would make a very thin rotor with a really long rotor, I will have mechanical problems, like vibrations, for example. And magnetic field strength, that's clear. I can use more wire on stator to create a stronger magnetic field. But as we have seen on magnetic materials, the limit is saturation. I cannot go stronger than 1.2, 1.5 Tesla. And also, this will be limited by the air gap. When we've done calculations of magnetic circuit, we have seen that basically the magnetic resistance of the magnetic circuit is given by the air gap size. So you can increase the torque by making the air gap smaller. Here is how the induction motor generates force. So here, those are the rotor bars and rings. And here, let's say I have a current that is flowing through this rotor bar. And this current is now in this magnetic field that is oriented in this direction. So this rotor bar will create me this force. Another rotor bar, the force will go into a different direction, but the sum of those forces created by the rotor bars will be what is creating me the force entirely. Now we will create the equivalent circuit of the induction motor. And the equivalent circuit will help us to understand the properties of the AC motor. It will help us to create the torque speed diagram, and we will also see what happens in the motor when we will change several properties in the motor, like resistance, for example. The equivalent circuit diagram is only a tool that helps us to understand this. It does not have anything in common with the real mechanical function of the motor. It's the same like for transformers. It helps us to understand it, but if you would connect it in this way, it would not create any motor. I will probably start directly with the schematics and we'll discuss individual properties. So we know that the rotor winding are the bars in the rotor. The stator winding are coils. So we will represent only a single phase of the stator winding as an inductor and a resistor. And we will recalculate the properties of the rotor to the stator. So here you see the equivalent circuit diagram. This part here is what is representing the stator winding. And this diagram is only for a single phase. So in a three-phase circuit, you would have this 3 times. So this is the inductor that is representing the stator winding. We can see that it has some inductance, and this is synchronous frequency. So we will represent this as a reactance in the circuit. This is the stator winding resistance, so basically the resistance of the wires. Here you see RC will be representing the losses in the magnetic circuit. XM will create the magnetizing inductance. So this will be what is creating the main magnetic flux in the motor. Is this schematic somehow familiar? Have we seen that somewhere? Oh yeah, transformer. So this is exactly the same thing like for a transformer. So the schematic is exactly the same like for a transformer. The only difference will be in how do we recalculate the rotor circuit. So far, this is like a transformer. And now, if I go back to the very beginning of my presentation here, let's say this. So now here I have a stator winding at this place, and I have a rotor winding at this place. So this is nothing else than a transformer. If I break the rotor and I take the voltage from the rotor to some load, it would be a transformer working from this winding into the rotor winding, and the amount of voltage that is being induced depends on the rate of change of magnetic flux. So for a transformer, we have used the factor that we called P, the transfer coefficient, saying the voltage in this one winding is being induced in the other winding. But here, for an induction motor, it will be a little bit more complicated, because now the rotor is turning and the rate of change of magnetic flux depends on slip. So in the equivalent circuit diagram, we will have a term S here that will recalculate the voltage based on slip. So this S hides the speed difference between the rotor and between the stator. And we can see that if I want to recalculate this voltage back to the stator side, I can multiply that by slip, and this will give me the voltage. The rotor is basically also a winding, either really the winding from copper wire or the squirrel cage. So it will have some resistance, it will have some inductance. Here, this is what is creating the resistance in my equivalent circuit diagram, and this is representing the rotor inductance. We can derive the equation for this circuit, and we can say that the stator winding voltage will depend on the magnetic flux, will depend on the number of turns, and here this is frequency and it's divided by square root of 2 because I want that this voltage is the RMS value. So this is the stator winding voltage that you will find over here. We can do the same for the rotor. So for the rotor, you see here we have the number of turns, magnetic flux, RMS, that's here we have square root of 2, and for the rotor we have seen that the induced voltage depends on the speed difference between rotor and stator. So here we can either write omegas here, or we can represent that by the synchronous speed times slip. Synchronous speed is given by the power supply frequency and construction, and slip is given by the load on the motor. It can be bigger than 1 if it's a brake. We will see that in the torque speed characteristic. But basically, if it's just a motor, it is from 0 to 1. Okay, so now what is it good for? We can represent the various properties of the induction motor as a function of slip. And this will help us to plot the speed characteristic. So, for example, the rotor frequency is synchronous frequency times slip. If the rotor is standing still, slip is 1, and the rotor frequency is the synchronous frequency. When the motor is speeding up, if it would speed all the way to synchronous speed, then slip would be 0. And induction motors are working close to 0 slip, even when it's unloaded. So this is, for example, the rotor frequency. For example, the rotor reactance will be given by slip times the rotor reactance. So this is recalculated rotor reactance to the speed of the motor. I will probably go to the final result, and the final result is that we can simplify this equivalent circuit diagram to something like this. Here we have the stator, so that's stator resistance and inductance. This is representing the magnetic circuit, and here we have the air gap, and the power is being transferred through the air gap, and this is what represents the rotor. And since we now have this circuit diagram, we can use it to plot the torque speed characteristic. So I will now show you a file that you have on the Moodle, and we will see what happens with different parts of the torque speed characteristic if we change the properties. So you can play with this Excel sheet yourselves. So now here that's a file where you can change the different properties of the motor based on the equivalent circuit diagram, and here you will see the torque speed characteristics. This plots 3 versions of the chart. We will see what will happen, for example, if we change the resistance. Here, this is slip from 0 to 1, which is here. So in this area, this acts like a motor. When slip is in this region, it will act as a generator. So you are trying to turn it faster than the synchronous speed, and it can produce power. And in this area, we will have the motor acting as a brake. We'll play with this file next week a little bit more, but now I want to show you the effect of those parameters on the torque speed characteristic. Here we have torque and current from the motor. Current, well, I will play just with this blue line. This is torque versus slip, and this is current versus slip. So we will see what will happen if I change the parameters. The torque speed characteristic depends strongly on the rotor resistance here. So R2, as represented in the equivalent circuit diagram, is the resistance of the rotor, and we will see it has a very big influence on the torque speed characteristic. So here I have some values. Let's say 6 ohms will give me this type of torque speed characteristic. What will happen, for example, if I choose 3? See the difference? Here I have increased a little bit the maximal torque, but this has changed the type of the characteristic. Let me probably do this. So now this green line is what was originally the 6, and this blue is what is the 3. So I have decreased the resistance in the rotor, for example, by using different material or by increasing the cross-section, it did not have that effect on the torque, but it had an effect on how sharp this characteristic is. On x-axis is slip. Slip, slip. The difference between synchronous speed and the actual motor speed. So when the motor is unloaded, it runs very close to this point, to synchronous speed, and when you load it, the speed is dropping a little bit. Here we see the effect of the rotor resistance. Here, this is, the blue is 3, so I have a motor with a small rotor resistance, which means the torque speed characteristic is harder. You load it, but the speed drops less to lower values. So if you have, for example, 6 ohms here, you see it's dropping faster, so I load it with the same torque and the speed is smaller. But as we will see on the current here, we will have a different current. For example, this is current here, and this is current here, and this magenta line is the current for 3 ohms. So we have a higher current in the motor. So the price that we are paying for having a harder characteristic here is that our motor is taking a higher current. For example, let's change this to 20. So now I have increased the resistance in the rotor. That's the blue line here. Now it means that this characteristic will be softer, so I load it and the speed drops more. But what was the gain here? Do you see a difference between the blue line here and between the green line here? Well, not that much. The maximum torque for blue line is somewhere around here, a little bit, yes. But there is a difference in some other position. Somewhere here. Here, at this part, we have slip 0. Slip 1. And slip 1 means it's standing still. So here, this value is startup torque. It means how much torque will be produced when the motor is standing still. So if I had this curve, which was now it's the 6 here, I had this hard characteristic, but I had this startup torque. If I would be able to add a resistor into the rotor circuit during startup, I could have a very high startup torque, and then I can switch back to, let's say, 6 ohms, and I could switch back to this characteristic. So there's a very big advantage of the wound rotor, that we can change the torque speed characteristic by changing the value of resistance in the rotor. If this is a squirrel cage motor, then you can't change anything. So for a squirrel cage motor, you have defined parameters, and this will give you some torque speed characteristic which you can't change. How about the other parameters? Let's say this is voltage, 300 volts. Let's say I will decrease that to 150. And to see the difference, I will use here the same values in all other positions. So here now we see the torque and current. And I will have here 150 volts only. So with 150 volts, I have also changed the shape of the torque speed characteristic. Here, this is the torque for 150 volts, 300 volts, and here this is for 150 volts. So I did not change the speed of the motor, but what I changed is the torque that the motor can produce. So here you can see that if I load it with the same torque, let's say in my case maybe 5 Newton meters around here, if I power it with 300 volts, I will have a significantly higher speed than for 150 volts. In fact, we will see that the torque that an induction motor produces is roughly proportional to the square of power supply voltage. So if I power that with 150 volts, I am expecting that the torque produced by the motor will be about 1/4 of the 300 volts motor. So you can change also the speed of the motor by changing the power supply voltage, but you are using the slip as an intermediate for that. It works in both ways. So if I would use 400 volts here, now you see a higher voltage will create me a higher torque that I can produce, and hence if I load it more, it will drop less with the speed. Let's test the other parameters. So let's go back to 300, and well, let's say for example this is the rotor resistance. So stator resistance. That's the stator resistance, 4 ohms. What will happen if I change it to 2? Not that much change. So what happens if I put 20? Well, 20 it's probably too much, but we see that here at this area we don't have that much of a change. So it doesn't make much sense to add a resistor in series with the stator winding. It will have an effect on the torque that it produces, but the effect is not that significant. The other parameters, like the inductance of the rotor winding, they have an effect as well, but there's no easy way how we could change the inductance in the real motor. So the only way how we can do that, how we can control the motor, is to have different rotor windings, for example. Okay, so let me review what we have seen today. We have seen how we can create an equivalent circuit diagram and how will this influence the characteristic of an induction motor. And next week we will discuss what are the losses in the motor and what are the efficiencies of such an induction motor. Some questions? Next week it's Easter Monday, so there is no lecture, no class next week. So we will have a lecture in 2 weeks, and we will finish some basics of the induction motors. Okay? See you in 2 weeks.